Okay, this is section 3.4, and we're going to look at a couple theorems, theorem 3.42 and theorem 3.43. Okay, so, and then some definitions that go along with those. So theorem 3.42, so any two bases for a given subspace contain the same number of elements. Okay, the same number of elements. So this is an important thing. Okay, so because it says, hey, if I have two different bases, I know they're the same size or the same number of vectors in them. And so they give a proof, pretty short proof. They say, okay, well, suppose we have two different bases. So, we've got x1 up to some xr is a basis, and y1 up to some ys is a basis. So these are bases of S. Well, then so they point out then the y's, so y1 up to ys. Now, by definition, they're bases, right? They form a linearly independent family in S, which is equal to the span. Okay, so we've got our x1 here up to our xr. So S, we know it's the span of the other vectors because they're a basis for it. And so from our work in 3.4.1, we know that we can make a basis out of this by doing the left-right thing. And so that S, so S has to be less than or equal to R by our left-right basis formation. But then, similarly, oh, I see they have a typo. Huh. Interesting. They say, oh no, by 3.3. I thought they said 3.3.2. I have a typo in my reading. I can't read. But anyway, so we know that S had to be less than R, but similarly, R has to be less than or equal to S, so S equals R. Okay. And so now that we've said that if we have any two bases of the same space, they have the same number in them, this is where they give us our definition. Dimension. Okay, dimension of a subspace S written dimension S like that is, they just say this number, okay, is the number of vectors in a basis of S. Okay, so it's the number of vectors you need to make a basis. And that's, so as we look at this, here's a remark. I don't know that they've made this remark yet, but a basis of S is the smallest linearly independent independent set of vectors that span S. Okay, so if I know I've got a linearly independent set, and they span S, then well, by definition, I guess I have a basis. So, in the idea here is, it's if I have anything smaller, it won't span S. Okay, so that's the idea. I can't have anything bigger and still have it independent. Okay, but if I take any set that's smaller that's linearly independent, it won't span S. So it's the smallest I can have. And they as part of, I guess I skipped this in the definition, the dimension of the set of the zero vector is 0. Okay, so that's an odd one in a way, right? But we don't have a basis for it, so it's an empty sort of thing. Okay, and so we have things like the dimension of Rn is n. Okay, because the standard basis for Rn would be n vectors. Okay, so then with that, we have the last theorem of this section 3.4.3, and it says a linearly independent set well, family they call it, independent family of m vectors in, they use the field M, so we could say Rm. And again, it's one of these things that I find, oh, wait, I'm sorry, I can't read again. A linearly independent set, linearly independent family of m vectors in, not Fn, they don't say, they say in a subspace S with the dimension of S equaling M must be a basis. Okay, and that goes back to the remark here, you know, that a basis of S is the smallest linearly independent set of vectors that span S. So if I know I've got dimension M, then dimension of S is M, then, you know, the proof is going to be based on that and the fact that all my bases are the same size. So they say let x1 to xm be a linearly independent family. Okay, so so there's our independent family that it was talking about. Guess they live off the grid or something. Okay, so we've got our linearly independent family of vectors in S, our subspace, where, so we're just setting this up with the aspects of the assumptions of the theorem. Okay, so linearly independent family of M vectors, so we have that in a subspace S with dimension M, so we've got that. And they say, well, we need to show that every vector of X every vector X in S, so general X's, is a linear combination of x1 to m xm. And so another way to say that is we need to show x1 up to xm span S. Okay, because they're already linearly independent. And so for a basis, right, they need to be linearly independent and they need to span S. Okay? And so they say, well, let's consider the following family of vectors. So they'll take some general X, let X be in S, and consider x1, x2, up to xm, and then toss on x. Okay, consider, and this would be a family of m plus 1 vectors. Okay. Now, if that's the case, this family, this new family, okay, this new family must be linearly dependent. Okay, and that is by theorem 3.3.2. Okay, so to remind you, and of course we use that in the last one. So let's go back and get the wording of 3.3.2. Remember that, you know, theorem 3.3.2 simply says a family of S vectors in the span of x1 to some xr is dependent, linearly dependent, if S is greater than R. Okay, so that was at least the important part of 3.3.2. See, and so we know that our basis has m vectors in it. Okay, we know that because where did it say dimension here is m. So we know that we have m vectors in the basis, and a basis spans the whole set, and so here when we did this one, added that x in there, we got m plus 1 vectors, and so that's too big. It has to be independent by theorem 3.3.2. Okay, and so since it's dependent, I kind of lost where I was here. Which one am I doing? 3.4.3. That was a close one. Okay, so since they're dependent, then I could find. Now their proof, boy, they mix a lot of x's in there. I don't like that. So, since it's dependent, I can write, so there exists. Okay, a backwards E like that, there exists A1 up to AM plus 1 such that they use X's, that's too many X's, such that A1 X1 plus A2 X2, oops, get rid of that line over the A2, A2 X2 plus AN XN, M, sorry, M, plus AM plus 1 XM, oh, no M on that one, XM, oh, didn't get rid of my eraser, X is equal to 0. Okay, the 0 vector. And with not all A sub I equals 0. Okay, so there's at least one that's not 0. And they say, well, okay, if A sub m plus 1 equals 0, that is a contradiction. Now, the reason that would be a contradiction is because the rest here, these would have to equal 0. So A1 X1 plus all the way up to AM XM would equal 0 with not all A sub I equals 0. Okay, but this would mean the X1 to XM are dependent. Okay, and they're not. We assume they're independent. And so that's a problem. So that can't be what happened. Okay, so a m plus 1 is not equal to 0. Okay, so if it's not equal to 0, then we can write x as a linear combination of the others. So x is equal to, what do we have? A1, x1 over am plus 1 plus, all the way to, well, actually those would be negatives, I guess. So we'll say minus and minus am over am plus 1 xm. So all I did was I came up here to this equation and I solved for x. And so that made all these negative, all the coefficients negative. I divided by the am plus 1, which I can do because it's not 0. And so x was any element of S. Okay, so the x1 to xm span S. Okay, because I could do that with any element x, and so I get this, and there we go. It's in the span. Okay, so I think so that gets us through all those theorems, right? And and so where this comes in handy is, so now an example, if I take well, I'll just do it as a set of vectors. So, whoops, there we go. So an example, suppose I have this set of vectors, 1, 0, 0, 1, 1, 0, 1, 1, 1. Okay, what I know is these vectors form a basis for R3. Okay, and the reason I know that is there are, 3 vectors, and the dimension of R3 is equal to 3. And then I also know those are independent. Okay, the vectors are linearly independent. And that, well, I know that because I've done a lot of these, right? If I go to reduced row echelon form of the matrix of these 3 columns, right, that'll be very simple. I can zero out that one by subtracting the second row. Well, actually both of those will zero out by taking the first row minus the second row, and then that one will zero out by taking the second row minus the third row, and I get to the identity. So I know they're linearly independent, and there are 3 of them, which matches the dimension of R3, so they form a basis for R3. And there we go.